This is video 13 in the series on concrete slabs. In this video, we will discuss some examples of how to use the method of equal deflection. First example is a slab, an isolated slab of type 3, which means clamped on opposite sides and simply supported on the two other opposite sides. And the question now is, for this general case, what is the formula for calculating the sagging and hogging bending moments? And what is the value of load that is distributed to the A direction and the B direction? Using the method of equal deflection means that the deflection at midspan in the B direction must be equal to the deflection in midspan on the A direction. And we know that the two loads, the load in A direction, the load in B direction, the sum of it must be the total load. And we know now, if you use those equations, that you have this simple formula, which is the load carried in the direction of B is the total load divided by 1 plus omega B, and omega B here is 5, divided by omega A, which is 1, and then B over A to the power 4. And for QA, it's similar, but there omega A, the first is 1, omega B is 5, and you have A over B. Then the bending moments, the sagging bending moment in the direction of B is the load times B squared over 8. The sagging bending moment in the direction of A is divided by 24, and the hogging bending moment in the direction of A is divided by 24. Now it's easy, just use QB in function of A over B, and the same for QA, and you just substitute it in the equations, and you simplify it, and then you have the following formulas. You see clearly that the bending moments, sagging and hogging, are proportional to the total load, or to the load in kilonewton per square meter, and the proportionality is just a geometrical function. It's only dependent on A of B. And for a square slab, that was also asked in the exercise, for a square slab A equals B, then we see that the sagging moment in direction of B is the total load. Q times 8 squared is the total load, is the total load divided by 48. The sagging moment in the A direction is total load divided by 28.8, and the hogging bending moment in direction A is the total load divided by 14.4. So you see that it is quite easy to use the method of the equal deflection. Now, let's check this. What we've got, we have to check it. So let's check it with a finite element method. And we use a slab of 20 centimeters depth. The size is 10 meters, A and B is 10 meters, and the load is 10 kilonewton per square meter. So we put it in our program, and then you will see you have the bending moments in the direction of X and the bending moments in the direction of Y. And you see that for the sagging bending moment in the direction of A, the finite element method gives you 31.8 kilonewton meter per meter, while the method of equal deflection gives you 34.7. You will see it's a little bit more, it's 10% more with the method of equal deflection, but this is expected because we know that this is a lower bound method. Then the hogging bending moment in the A direction, that's the dark blue, it's with the FAM model, it's 70, and for equal deflection, 69, so it's equal. And the sagging bending moment in B direction is 21.6 for finite element method and 20.8 for equal deflection. So you see that the method of equal deflection is an easy method of estimating the maximum bending moment, and it is quite accurate. Let's take a second example. This time it's a square, it's a rectangular slab with a side of 6 meters and 4 meters, and the two adjacent sides are clamped and two other adjacent sides are hinged. The total load is 15 kilonewton per square meter, and once again, what is the load transferred in the direction A and what is the load transferred in direction B, and what are the formulas for the hogging and the sagging bending moments. We can use the general formula. The load transferred in direction A is the total load divided by 1 plus omega A divided by omega B times A over B to the power 4, but it's symmetrically, so omega A is equal to omega B, so this is 1, and the load transferred is 2.47. The bending moment, the sagging bending moment in the A direction is then using the simple formula for like we know from applied mechanics. Then you see that for the sagging moment it's 6.25 kilonewton meter per meter. The hogging bending moment is then the load times the span squared divided by 8, and it's 11.11 kilonewton meter per meter. So in a very short time, with small efforts, you can immediately calculate the bending moments. In the other direction, the load transferred in this direction is 15 divided by 1 plus omega A is equal to omega B. So, and this is B divided by A, because we are calculating the load transferred in direction B, is 12.53. The bending moment is then 14.10, and the hogging bending moment is then 25.06. We see also that the sum, always the sum of the two transferred loads in the two directions must be equal to the total load, which is 15. Third example, it's a rectangular, size 7.6 and 5.7, simply supported on all sides. And here we know that the depth of the slab is 250 millimeters, the concrete grade C2530, the concrete cover 30 millimeters, tiles and mortar on top of the floor is 3 kilonewton per square meter, and the mobile load is 5 kilonewton per square meter. And now we are trying to calculate the needed reinforcement without taking minimum reinforcement into account, and we have to use the method of equal deflection. We start with the load in the A direction. This is the general formula. We know now that because it's simply supported on all sides, so omega A is 5 and omega B is 5. These are the lengths, A 7.6 and B 5.7. The total load is 1.35 times the permanent load, which is the proper weight and the finishing of the floor, plus the mobile load times 1.5, and it gives you 20 kilonewton per square meter. That's the total load in ULS persistent. The amount of load, the part of a load that is transferred in the A direction is 4.81, in the B direction 15.19. So the sum of the two is 20, so that's all right. The lever arm in the A direction. Now we have to consider what reinforcement is situated in which layer of reinforcement. It is recommended to put the reinforcement in the first layer corresponding to the highest bending moment, which is logic. So we know in the A direction, that this is not the highest bending moment. So that's why we use here the lever arm in the second reinforcement ratio. So it is the depth, total depth of the slab minus the reinforcement, minus the concrete cover, minus the first layer of reinforcement. We assume diameter 12. If this is not the case, we have to recalculate it. So we assume diameter 12 and then the center width of the second layer, it's 12 divided by 2. So the lever arm is 202 millimeters. The bending moment is the load times the span squared divided by 8 is 34.7 kilonewton meter per meter. And then with the tables, the concrete tables, you can find that the needed reinforcement for the sagging bending moment in the direction of A is 413 square millimeters per meter, or it means diameter 12 at 250 center to center. The lever arm for the first layer of reinforcement is the total depth of the slab minus the concrete cover minus the center width of the first layer. It gives you 212 millimeters. The sagging bending moment is then 61.69 kilonewton meter per meter. You see this is bigger than the 34. That's why we chose to put the reinforcement in the B direction in the first layer of reinforcement. And then the needed reinforcement through the tables of concrete calculation, we find that it's 704 square millimeters per meter, or diameter 20 at 150 millimeters. Another example, again, the same slab as the previous example, but now we will calculate it with the method of Marcus. So for the method of Marcus, we have to use a correction factor to the bending moment that you obtain with equal deflection. This correction factor looks like this, and capital Mx is equal to Q8 squared divided by 8. We know the value of A and B. We know the total load, which was 20 kilonewton per square meter. The load transferred in direction of A stays the same as the previous exercise, which is 4.81. In the direction of B, 15.19, and the sum is 20, so that's fine. The bending moment for equal deflection in the direction of A was 34.73, or with the formula, or like the example 4 that we have just had. The capital A bending moment is then 144.4, and the correction coefficient, nu A, equals then 0.6437. It is just using this formula, nothing more, nothing less. And then the actual bending moment in the direction of A is then the correction factor times the bending moment obtained by equal deflection, and it gives you 22.36 kilonewton meter per meter. You see that nu is smaller than 1, and the correction is downwards. Then we do exactly the same for the direction of B. It's the same method, and we obtain a bending moment equal to 69.73 kilonewton per meter. You notice that the correction factor in A and B direction is almost the same. We can also use the general formula for the method of Marcus. Sometimes it's easier to use. This was the formula for the factor Ka, and alpha A and alpha B was 8, and omega A and omega B was 5, and T is A over B, and then it's 7.6 divided by 5.7, and it's 4/3. So T is 4/3. We know all the variables in this equation, so it's easy to calculate it, and we find that Ka equals 0.019. And The value for MB, for the bending moment in the B direction, is exactly the same formula, but we use cyclic permutation, of course. A becomes B and B becomes A. We fill this in and we have 0.06114 from KB. Then the bending moment in the A direction is the correction factor plus the total load times A squared is 22.35. And the lever arm in the A direction, again, this is the second layer of reinforcement. You see that I'm using, it's normally a guess, 12. Normally I should have used here also 12, but I've done the exercise before, so I already corrected it. So in principle, you have to guess the diameter and then correct the diameter accordingly. So the reinforcement is then 262 or diameter 10 every 250 millimeters. You see, that's why there is 10. Normally you put 12 here. You do the calculation, you find that the distance between the diameters 12 is too big. So you know you have to lower the diameter of the reinforcement, and then you have to recalculate this, and you make it instead of 12, 10, and then the center to center distance of the reinforcement is okay. It should always be smaller than 1.5 times the thickness of the depth of the slab. In the B direction, we have the correction factor of 0.06 in the B directions times the total load and the distance in B squared. It gives you 39.73. The lever arm is diameter 12. We have 446 square millimeters per meter, or diameter 12 or every 250 millimeters.